Good morning, everybody. Going to give everybody 1 minute to join in before we start today's fascinating lecture on simple harmonic motion.
I don't know if it's in my computer charger anywhere. I don't know where it is. I don't need it right now, but it's right here. It is right here.
All right, give people just 30 more seconds. Got 19 people. Let's see if we get 25. Oh. All right, seem to be holding steady. And I apologize if it's a little loud. They're doing yard work right outside my house. Hopefully that's not going to be too big of an issue. So let's start with a little recap. Okay, so keep in mind, simple harmonic motion, we are using a simple model of a mass connected to a spring constant K, oscillating back and forth on a frictionless surface. And I mentioned before, it's not that spring mass systems are so important, but they illustrate simple harmonic motion, and there's many different systems that undergo simple harmonic motion. And so for a spring mass system, the only force acting in the x direction if there's no friction is just the force the spring exerts, negative kx, which equals ma. If I write acceleration as the second derivative of position with respect to time, what I get is second derivative of position with respect to time is negative k over m times x. This is a differential equation if you haven't had differential equations before. And it's specific for the spring mass system. But let me go a different color here. Let's do green. Any system where the acceleration is negative some constant times the position is going to undergo simple harmonic motion. And we'll see once we get to pendulum that it also applies for pendulum swinging back and forth. So the solution to this differential equation is some function that when I take two derivatives of it, returns the original function times some constant, sine or cosine. We choose cosine for position. So position as a function of time is A, which is the amplitude, times the cosine omega t plus phi naught. Omega is called the angular frequency, and it equals 2 pi times the frequency, or 2 pi divided by the period. That's going to be true for any system undergoing simple harmonic motion. For our spring mass system, I showed that omega is equal to the square root of k over m. That's only true for a spring mass system. If I want the velocity versus time, I can take the derivative of position versus time, and I get negative a omega sine omega t plus phi naught. And if I want the acceleration versus time, I take the derivative of the velocity. I get negative a omega squared cosine omega t plus phi. Phase angle describes the initial conditions of the system, describes the initial position and the initial velocity. And a couple things to keep in mind about the phase angle. If the phase angle is positive, that means the curve is shifted to the left. If the phase angle is negative, it means the curve is shifted to the right. So looking at this a little bit more detail, one of the things you should know is how position, velocity, and acceleration are related. So one, these equations, I took this from a different book. That book was just using xm for the amplitude. And instead of theta naught, they were just using theta. Same thing. So my position versus time and all of these plots assume a phase angle of 0. So position versus time is just a cosine curve, a cosine omega t plus phi naught. Velocity versus time, in this case, is a negative sine curve. negative a omega sine omega t plus phi naught, and acceleration versus time, negative a omega squared cosine omega t plus phi naught. Again, notice that my acceleration versus time, in essence, is my position versus time flipped upside down times some constant. So again, for these equations, omega, angular frequency is 2 pi times the frequency, or 2 pi divided by the period. And for a spring mass system, omega is given by the square root of k over m. So our frequency and period we can get from that. And I mentioned one really cool thing is that the frequency and the period is independent of amplitude. So if I pull the spring a certain distance and let it go, it'll oscillate back and forth with a certain period. But if I pull the spring twice as much and let it go, the frequency and the period are going to be exactly the same. It does not depend upon amplitude. Okay, so that was kind of oh, and the last thing was energy in simple harmonic motion. So we are just dealing with simple harmonic motion with the object oscillating back and forth horizontally. If the object was oscillating vertically, then I would also have to look at the gravitational potential energy, but we're not doing that. So if I have the object oscillating back and forth and there is no friction or air resistance, the only two forms of energy are the elastic potential energy stored in the spring and the kinetic energy of the moving mass. So my total energy is just 1/2 mv squared plus 1/2 kx squared. Or again, I'm just using x instead of delta x. This is always going to be true at any point in the motion. But when the object is at plus or minus the amplitude, the speed is 0 for a split second as it's changing direction. So all of the energy is elastic potential energy, 1/2 kx squared, and x is plus or minus a. As the object is crossing the equilibrium position, the spring is not stretched or compressed, which means there is no elastic potential energy. All of the energy is kinetic energy, and it's moving its fastest as it's crossing the equilibrium position. So two other forms of the total energy, 1/2 Ka squared and 1/2 mv max squared. And that was sort of it for a little recap. So going to speaker view, recap. Oh, where's my other hat? Recap. Oh, before I take it off, let me just open it up real quick. What questions can I answer about anything I've covered so far in chapter 15? I'm going to do a couple example problems right after this, but before I do, questions I can answer.
I have a question. For the equation for energy,
Yes.
is it just V max? Do you only use the V max in your equation for energy when x equals 0, or is it always the maximum velocity that you use?
So those three different equations, let me share that real quick, will always apply. So if I'm given the speed and the x at any point, I could use this top equation, 1/2 mv squared plus 1/2 kx squared. That always applies.
Okay.
But at the amplitudes, at x equals plus or minus a, it's at rest for a split second. So the total energy is also 1/2 Ka squared. And when it's passing through the equilibrium position, the spring is not stretched or compressed, but that's when it's moving the fastest. So all three of these energy equations apply, and it's going to depend upon whether you know what the amplitude is, what you know what the max speed is, or if you're given x and v at a given point. And I'm going to do an example problem like that in just 1 second.
Okay. Thank you.
You are welcome. Any other questions I can answer before I move on? Okay. Let me start with a clicker question. So, clickers. One of the things you should be able to do is relate position, velocity, and acceleration. So if I gave you a position versus time curve, you should be able to tell me stuff about velocity and acceleration and so on. So question 15. The position of a mass on a spring as a function of time is shown below, and all shown to the right. At the time corresponding to point P, what are the signs of the velocity and the acceleration? So here's a plot of something in simple harmonic motion. And this is just a plot of position versus time. The question is, what is the velocity and the acceleration? And let's do this as a poll. So if you have, if you're watching this on a computer, I've just launched a poll. If you're watching this on a phone, you may not be able to see it. But as a clicker question, what do you think in terms of velocity and acceleration? Is velocity positive or negative? Is acceleration positive or negative? What do you think? Ooh, we got a bunch of people saying D. A few people saying B. Give it another 15 seconds for people to respond if they want. What is the sign of the velocity? What is the sign of the acceleration? You can see it on the phone. Oh, you can see it on the phone too. Excellent. All right, another 10 seconds. Punch in an answer if you want. Ooh, 28 out of 29 voted. Oh my God, 100% voted. Woohoo! Let's end the polling. Share the results. All right, we've got 76% of you say D, 24% say B. Well, everyone got that the velocity is positive. So if you're given a plot of position versus time, you know the slope of position versus time is velocity. At point P, the slope is positive, so I know that my velocity is positive. Now, how about the acceleration? Easiest thing to keep in mind is acceleration is always, for simple harmonic motion, negative some constant times the position. So in this case, my position is positive, which means my acceleration is negative. So the correct answer is the velocity is positive, the acceleration is negative. One other question before I move on, just as a follow-up. One of the other things you should be able to do is figure out what the phase angle is. So the question here is, what is the phase angle for this particular graph, for this particular object moving back and forth? And the way you think about this is, I know, let me make this a little smaller, that my position versus time is equal to A cosine omega t plus the phase angle, which means at t equals 0, my position at t equals 0 is going to be equal to A cosine of the phase angle, because I'm plugging in t equals 0 for the time. So in this case, at x equals 0, I'm sorry, at t equals 0, two things you need to know. What is x and what is the sign of the velocity? So here x equals 0 and my velocity is greater than 0. I know my velocity is greater than 0 just because the slope right here is positive. So what I'm doing, I'm solving for x at t equals 0 is 0 equals A times the cosine of the phase angle, which means my cosine of the phase angle has to be equal to 0. So my phase angle is the inverse cosine of 0. You plug that into your calculator, and what it's going to give you is pi over 2. But cosine of theta is the same thing as cosine of negative theta, which means my phase angle is going to be plus or minus pi over 2. Now, which one is it? Here's where looking at the sign of position and velocity is useful. So let me go back to this applets. And I was kind of showing, let me just real quick share this new share. So remember, the whole interesting thing about circular motion and simple harmonic motion is a projection of circular motion as this is moving around in uniform circular motion. So as this red dot is moving around at some angular speed, omega in radians per second, if I look at the x component as it going in circular motion, that really describes an object in simple harmonic motion moving horizontally back and forth. So in the first quadrant, we had x is greater than 0, but the thing is moving to the left, so the velocity is negative. In the second quadrant, x is less than 0, the object's still moving to the left, so the velocity is negative. third quadrant, oops, do third quadrant again. Third quadrant, x is still less than 0, but now the object is moving to the right, so the velocity is positive. And then in the fourth quadrant, the object is to the right of the origin, so x is positive. It's moving to the right, so v is positive. So going back to this, really good to know this, that in the phases, in the first quadrant, x is positive, v is negative. Second quadrant, x is negative, v is negative. Third quadrant, x is negative, v is positive. Fourth quadrant, x is positive, v is positive. So going back to this one, we know we want the velocity to be positive, which means that I'm going to have my phase angle to be negative pi over 2. So that I'm in the fourth quadrant where x is positive, v is positive. Okay, let's do an example problem.
Wait, can you go back to that, to the, where you write all that out?
Right there. So we were looking at a case where we knew the position was positive and the velocity was positive, so we know the angle had to be in the fourth quadrant. If instead the position was positive and the velocity was negative, then it would have been in the first quadrant. We would have chose pi over 2. Okay. So this is example problem 1516. And this is a really good example problem for just going through everything. So it really contains a lot of the information. So a 200-gram mass attached to a horizontal spring oscillates at a frequency of 2 Hertz. At t equals 0, the mass is at x equals 5 centimeters and has a velocity of negative 30 centimeters per second. Determine the period, the angular frequency, the amplitude, the phase constant, the maximum speed, the maximum acceleration, the total energy, and the position at t equals 0.4 seconds. Whew! A lot of stuff. But if you understand this, this is much of this chapter. So one, let's just write down what we're told. We know the mass is 0.2 kilograms. We're told the frequency is 2 Hertz. And we're told the initial position at t equals 0 is 5 centimeters. And the initial velocity at t equals 0 is negative 30 centimeters per second. And then we want to know pretty much everything about this system. So A, determine the period. Well, keep in mind that period and frequency are inversely related. So I know that my period is just going to be 1 over the frequency, which will be 1 over 2 Hertz. So my period is just half a second. Pretty straightforward. B, what is the angular frequency? Angular frequency omega is always going to be given by 2 pi times the frequency. This is true for any system undergoing simple harmonic motion. Omega, angular frequency, is always related to the linear frequency, how many times per second it oscillates back and forth, by this equation. So we've got the frequency is 2 Hertz. And so my angular frequency is just going to be 4 pi radians per second. Remember, radian is not a real unit in terms of, it's really just a distance divided by another distance. So it doesn't have a unit like normal units. C, the amplitude. So here's a case. Anytime you're given the position and the velocity at a given time, you can use conservation of energy to figure out what the amplitude is or what the maximum speed is. So I know my energy at any time, the total energy is just the kinetic energy plus the elastic potential energy. And I know it's also equal to 1/2 k a squared. or 1/2 mv max squared. Always going to be true. So here's a case where I'm given the mass, I'm given the speed and the position at a given time. So if I knew what k was, then I could solve this equation for the amplitude. I was not directly given what k is. However, I know that for a spring mass system, k is given by the square root of, omega is given by the square root of k over m. So if I have m and I have omega, I could solve for k. So omega squared equals k over m. So k equals m times omega squared. If you're going to use this equation to solve for the spring constant, m must be in kilograms, omega must be in radians per second. So what I get is 0.2 kilograms times 4 pi radians per second squared. And what you're going to get is k is 31.6 newtons per meter. Now I can use conservation of energy and say that 1/2 mv squared plus 1/2 kx squared equals 1/2 ka squared. And just for timing, let me just skip the algebra. We have everything in this equation except for the amplitude. So all we're doing is just solving this equation for the amplitude. And what you're going to get once you solve it, and this is assuming the book answer is correct, which is not a great assumption sometimes, is 5.54 centimeters. And again, that was just from taking this equation for energy and solving for the amplitude. Now, I could have also done this and solved for V max if I was instead asked for the maximum speed. Let's take this down a bit. D, the phase constant. So again, anytime you want the phase constant, you're looking at what is the initial position. You're going to solve for the phase constant. And you're going to get two different values. You need to figure out which value to use by the sign of the velocity. So we know at t equals 0, my initial position is 5 centimeters. And we just solved for the fact that the amplitude is 5.54 centimeters. So position as a function of time is a cosine omega t plus the phase angle. My position at t equals 0 is going to be a times the cosine of the phase angle. So in this case, what we get is 5 centimeters, which is my position at t equals 0, equals 5.54 centimeters, which is my amplitude times the cosine of the phase angle. So cosine of the phase angle equals 5 centimeters divided by 5.54 centimeters, which is 0.903. So my phase angle is the inverse cosine of 0.903, which is going to give you plus or minus 0.45 radians. So here's a case where I have x is greater than 0, but my velocity, remember, we were told was negative 30 centimeters. So I want my velocity to be negative. So I want a positive position, a negative velocity, which means I want my phase to be in the first quadrant. So I'm going to have, for my phase angle, it's going to be 0.45 radians. If instead the velocity was positive, then I would have had my phase angle as negative 0.45 radians. Oh, it's taking up a lot of space. Okay. What is the maximum speed? So for these, I'm just going to detail how you would do it. Two different ways that we could figure out the maximum speed. One, I know my maximum speed is given by the amplitude times omega. I've got the amplitude, I've got omega, I could just solve for that. I could also use conservation of energy and say 1/2 mv squared plus 1/2 kx squared equals 1/2 m times v max squared. Either one of these is going to give you the exact same answer. The first one is obviously the easier one algebraically. We know the amplitude is 5.54 centimeters. We found omega was 4 pi radians per second. What you'll get is that your maximum speed is, again, assuming the book is correct, 70 centimeters per second. What else do we have? F. What is the max acceleration, the total energy, and the position? All right, so for F, we want the maximum acceleration. Easiest way to figure this out, maximum acceleration equals a omega squared. Again, I have the amplitude, I have omega. Let me just skip writing out the numbers, which you'll find when you plug in 5.54 centimeters for the amplitude, 4 pi radians per second for the omega is 8.8 meters per second squared. Let's move this down more. G, what is the total energy? Well, easiest way is I know what the amplitude is, so I could use my total energy is 1/2 Ka squared. I also know what V max is, so I could use 1/2 m V max squared. Again, I've got K, I've got A, I've got M, I've got V max. I could use either of these equations. If you plug in the values, what you should find is that the total energy is 0.49 joules. And then last but not least, H. And this is a great part. You want to know what is the position at t equals 0.40 seconds. Now, how are you going to get the position? Well, I know I have a general equation for position as a function of time as A cosine omega t plus the phase angle. Well, I have A, I have omega, I have the phase angle. So my position as a function of time is going to be 5.54 centimeters times the cosine of 4 pi radians per second times t plus the phase angle, which we saw was 0.45 radians. So plus 0.45 radians. So all I have to do is plug in t equals 0.40 seconds into this equation, and out it's going to pop my position. Again, let me just skip plugging in the values, but you're just plugging in 0.4 seconds for t, evaluating the cosine of whatever this expression turns out to be, multiplying it by 5.54, and what you're going to get is x equals plus 3.8 centimeters. So this is a really good problem. You would be expected to know this for sort of the upcoming quiz, and it would probably be, you know, a couple different problems if I gave you something like this. One problem might be answering what is the period and what is the angular frequency. Another part might be what is the amplitude, things like this. All relatively straightforward, but just understanding how everything fits together. Okay. Next thing I want to go through is just something that you are definitely going to need in physics 4B. You're going to use it all the time. You may have had this before in math class, but let me just check on this quick little chat. Can I see part H? Let me go back to this real quick. Part H. So again, if you wanted to know, let's say, position or velocity or acceleration at a given time, then what you're doing is really you have equations for x, for v, and for t. Once you know what the amplitude is, once you know what the angular frequency is, and once you know what the phase angle is, then you can literally just plug and chug, put a time in, and you could get what the position versus time, or get the position at that time, you can get the velocity at that time, and you can get the acceleration at that time. All right, so small angle approximation. And I really like this because, well, I'll tell you in a second, but what you think of a small angle is not. So one, this is the Taylor expansion of sine, which if you haven't had it yet, don't worry about it. But if you were to take sine of x and expand it, what you get is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th plus blah, blah, blah. This is infinite sum. Well, here's the thing. If x is a really small number, meaning much, much, much less than 1, if I take a small number and I square it, I get a really, really small number. If I take a small number less than 1 and I cube it, I get a really, really, really small number. So from this expansion of sine theta, which again, if you haven't had series yet, don't worry about it, but I think most of you had, then if theta is less than 1, much less than 1, then theta cubed over 3 factorial is going to be unbelievably small. Theta to the 5th over 5 factorial is going to be unbelievably small. And so if theta is much, much less than 1, then I can approximate sine theta being about equal to theta. And the reason is because this x cubed term, this x to the 5th term, the x to the 7th term, the x to the 9th term, they are going to be unbelievably small, right? Just for example, if I take a number like 0.1 and I square it, you know, 0.1 squared is 0.01. 0.1 cubed is 0.001. And I could just keep going. So if I have a number which is small, like 0.1, the next term in the series would be 0.001, and then I'm dividing that by 3 factorial and so on. So if my angle is really small in radians, then I can approximate sine theta with theta. Now, what does really small mean? Is 20 degrees a small angle? And believe it or not, it depends upon how accurate you need to be. But let's just do this approximation. 20 degrees, if I convert into radians, is 0.3491 radians. Right? Remember, there's 360 degrees in a complete revolution, 2 pi radians in a complete revolution. So if I ever want to convert from degrees to radians, I'm multiplying by 2 pi radians divided by 360 degrees. So 20 degrees, 0.3491 radians. My small angle approximation says the sine of my angle is about equal to the angle for small angles. Now, so in this case, the approximation says the sine of 0.3491 radians is about equal to 0.3491. If you plug into your calculator the sine of 0.3491 radians, what you get is 0.3420. This is only a 2% difference. So even something like a 20-degree angle, once I convert that into radians, it's not much, much, much less than 1, right? 0.3491 is not much, much less than 1. But that only gives me a 2% difference between the approximation being that the sine is equal to the angle and the real value of the sine. Now, for something like 10 degrees, the approximation gets even better. Now, so what I tell people generally in using small angle approximation, if the angle in degrees is less than about 20 degrees, and again, you have to convert it to radians, but less than about 20 degrees, you can use the small angle approximation and your percent error is going to be less than a couple percent. Okay, you will use that in 4B a lot. Where it comes up in physics 4A is a simple pendulum oscillating back and forth. And what I think I'm going to do is just cut to the chase and tell you the results that you need to know. I'll just touch on the derivation, but we're going to only look at a simple pendulum. And a simple pendulum is a mass M suspended from a massless, unstretchable string of length L. So a simple pendulum is just a mass on a string. String is a length L, the mass is M, and it's just oscillating back and forth. And what I'm going to show you is you need to use the small angle approximation when you're deriving this equation for pendulums, which means it's only true if the pendulum is swinging back and forth at relatively small angles. So don't worry about this derivation. I'm going to go through it kind of quickly. The point that I want to get to the end is that omega for a simple pendulum is given by the square root of G over L. Remember, for our spring mass system, omega is the square root of K over M. And we kind of got that because acceleration was equal to negative K over M times a position. And that's really the hallmark of simple harmonic motion, is acceleration is some constant, which ends up being omega squared times the position. So for this, we're looking at circular motion. And what we know is that sum of the torques on an object equals I, which is the moment of inertia, times alpha. Well, the only force acting on this mass as it's swinging back and forth that's exerting a torque is the force of gravity mg. Now, tension's also exerting a force, but the tension is not exerting a torque because the angle between the tension and torque is not rewinding. I do have the tension in the rope exerting a force, but it is not exerting a torque on this mass. The torque is from gravity. You know what? Just thinking about this, let me just cut to the point. Is if you go and analyze the sum of the torques equals I alpha, what you're going to get is this equation that says the angular acceleration is negative LmG over I times the angle theta. And you need to use the small angle approximation for this. This is pretty much of the form A equals negative omega squared times x, but in angular quantities. So instead of linear acceleration, we have angular acceleration, and instead of x, we have theta. Well, that means that for this system, omega squared equals LmG over I, or omega is the square root of LmG divided by I. And for a mass just connected to a string that has no mass, the moment of inertia is ml squared. But key point is this. Angular frequency for a pendulum swinging back and forth at small angles is the square root of G over L. And the way we end up using this is, since frequency is related to omega, omega is 2 pi f, I can solve for the frequency and get that it's 1 over 2 pi the square root of G over L. Period, which is 1 over the frequency, is 2 pi the square root of L over G. One interesting thing, this does not depend upon the mass. And let me just tell you that we have actually used equations like this, the period equals 2 pi times the square root of L over G, to search for oil. How does that work? Well, let's say I had a really sensitive pendulum, and I could time how long it takes to go back and forth. That's the period. Well, if I know the period and I know L, I could solve for G. And so one of the ways they prospect for oil, and it's not really using a pendulum swinging back and forth, but it's something that depends upon the value of G. And when there's a large deposit of oil, the acceleration due to gravity at that local location will be slightly different. So one of the ways you can prospect for oil is by going to different spots on the Earth, measuring something that depends upon the acceleration due to gravity. And if you get the value of G locally being different than in other locations, that tells you that the density of the Earth at that location is different. Interesting point. Was about 2 years ago, weirdest thing, I woke up and apparently I got abducted by aliens in the middle of the night. And I was just placed in a blank room, and all I had on me was my watch and some sneakers. I was dressed. And I did not know whether I was still on the Earth or whether I had been transported to a different planet. And I needed to figure it out right away so I could call for help if I needed to. Well, the way I figured out if I was still on the Earth or on a different planet is I made a simple pendulum out of my shoes, and I just let my sneakers swing back and forth. I measured the period. I knew about how long these shoelaces were, and so I solved for the acceleration due to gravity, and it ends up that I wasn't transported to another planet. I just couldn't even go through with that. So just two interesting things. One, the pendulum's period does not depend upon the mass that you hang off the end. It only depends upon the length and G. And in fact, this is how grandfather clocks worked, right? You've got this thing that's just swinging back and forth. And as long as the oscillations are small, then the period does not depend upon the amplitude, does not depend upon the mass hanging off the end. I like the story. So the moral of the story is, if you find yourself in a room, possibly abducted by aliens, and you don't know whether you're still on the Earth or on another planet, you can make a simple pendulum out of your sneakers, measure the period of sneakers moving back and forth, look at how long it is, you can solve for G. If it's 9.8 meters per second squared, then you know you're still on the Earth. Okay, very last thing I want to talk about conceptually, PowerPoint, is this cool thing called resonance. And this comes up in so many different things that you'll talk about this in Physics 4B. There's lots of interesting applications. So every time a system is set into motion and left to just go on its own, it's going to oscillate back and forth at some natural frequency. We call these free oscillations, and in essence, it's kind of like the frequency that an object wants to oscillate back and forth at. So we've seen a couple. One, we know that for a spring mass system, frequency is 1 over 2 pi the square root of k over m. And I know that for a pendulum, well, for anything, omega is 2 pi times the frequency, which we solved for omega was the square root of g over L. So you can get the frequency. So if I had a pendulum and I just pulled it to the side and let it go, it would naturally swing back and forth at a certain frequency. If I had a mass on a spring, I pulled the mass aside, let it go, it's going to oscillate back and forth at a certain frequency, called its natural frequency. Whoa. And that is the frequency that it naturally wants to oscillate back and forth at. So if you go to a playground and you have a swing, you could figure out what the period of that swing is going to be, or what the frequency of that swing is going to be. It's only going to depend upon the length of the swing and the acceleration due to gravity. So I take my daughter to the park, pull her up, let her go. She's naturally going to oscillate back and forth at a certain frequency that's only going to depend upon the length and G. Well, could I make an object oscillate at a different frequency other than its natural frequency? And the answer is yes. If I push my daughter on the swing at a certain frequency, I can make her oscillate at that frequency. That's called forced or driven oscillations. So I'm forcing something to oscillate at a given frequency by exerting a force on it. Or, you know, if I have a mass connected to a spring, I could keep exerting a force on that mass at a given frequency and make it oscillate at that frequency. Well, here's what resonance is, and it's a very cool concept, is if I match the frequency of my driving force to the natural frequency it wants to oscillate at, I can cause this dramatic increase in amplitude, and that's what resonance is. It's a dramatic increase in amplitude that happens when the frequency of forced oscillations, or the frequency of them driving it at, matches the object's natural frequency. So if you're thinking about, you know, pushing a child on a swing, if you're not paying attention and you just push randomly, sometimes you're going to be helping them out and make them swing higher, sometimes you're not. But if I time my pushes at just the same frequency that this thing wants to oscillate at, even the tiniest force can cause this dramatic increase in amplitude. And what I want to do is show you some cool videos that have resonance phenomena in it. So again, everything has a natural frequency that it'll tend to oscillate at. And we didn't really cover sound very much, but if I drop a pen, every time I drop a pen, it makes the same sound. And that's because even an object like a pen, if I strike it, it's going to naturally oscillate at a certain frequency, and the sound it emits is going to be the same as the frequency it oscillates at. That's why tuning forks work. Tuning forks, every time you hit them, they oscillate back and forth at that exact same frequency. That's their natural frequency. Well, if I exert a force on it at that exact same frequency, I can cause the amplitude of the oscillations to increase dramatically. So let me share with you some videos. I hope this works. So one, even a piece of glass, a glass has a natural frequency. And if you've ever seen a singer shattering a glass, what's happening is the frequency of their voice exactly matches the natural frequency of the glass. And it's like pushing a child on a swing, very small pushes, but you're timing it just right, so it just keeps swinging higher and higher and higher. So let me see. Holy schmoly. Let me just, I'm not sure if that's sharing. Let me stop this for a second. That. Do share screen again. Go back.
In 1940.
Okay, wow, that's really loud. So this, here's a little history lesson. Way before DVDs and Blu-rays and things like that, we used to record music on cassette tapes. And Memorex was sort of the brand. And Memorex's big tagline is it real or is it Memorex? And it was basically implying that recordings on Memorex cassette tapes are so good that you can't tell the difference between a recording and the actual thing. So they had a commercial where Ella Fitzgerald, who's a jazz singer, was singing, broke a wine glass, and then they recorded it and broke a glass using her recorded voice. But can I do this? So let me play it once and then I'll just show you in slow motion. So notice. So it's hard to see, but this is her voice breaking the wine glass. And then they record it, and notice they're breaking a different glass altogether. They're breaking a beaker. If this really was a perfect recording, then the recording should be able to break the exact same type of glass that her voice did. My guess is the recording is not perfect, and so the frequency didn't exactly match her voice, and so the recording couldn't break the glass, so they had to find something else that it could break. Not that. Okay, so one, here's what it looks like as a glass breaks. I'll just kind of go. So you've got these sound waves that you can't see that are basically hitting the glass at just the right frequency, causing the glass to start to oscillate back and forth in bigger and bigger amplitudes until eventually you can break the glass. So this is just sound waves that you can't see that match the frequency of the glass, cause the glass to shatter. All right, another one. So you may have heard of Tacoma Narrows Bridge. So there was a bridge in Washington. Everything has a natural frequency, even bridges. And so what ended up happening was there was this wind. this wind was hitting the bridge at just the right frequency, causing the amplitude of the bridge swaying to increase. And this is just from the wind, and it's not even that strong of a wind. It's not like it's 100, 200 mile an hour wind, causing this thing to oscillate back and forth. Pretty amazing. And eventually,
in
it did
1940,
collapse.
the 4-month-old Tacoma Narrows Bridge, nicknamed the Galloping Gertie, was set into resonant vibrations by a 40 miles per hour wind. Initially, the bridge vibrated in a transverse mode, but later in a torsional mode, and eventually it collapsed.
So, wind hitting the bridge at just the right frequency, causing the bridge to start to oscillate more and more and more. Over time, the amplitude built up to the point where the bridge collapsed. So here's a really interesting one I found on military.com. So I'm just going to play this and let you see it. It's kind of interesting. Even something like a helicopter, or in this case, the spinning part, has a natural frequency that it tends to oscillate at. As this blade is slowing down, at some point it's rotating at just the same frequency, which causes the amplitude to increase to the point where, bam. Right, really glad they're testing this out. Okay, last video I'm going to show you, I renamed to Mystery, so that you can tell. So let me just say, this is an example of resonance. I'm going to play it once, see if you can figure out what this is. Looks like a fortune cookie, but it's not. Let's go back, give you a hint. It is a medical procedure. Anybody have a guess to what it is? The medical procedure that incorporates resonance. Let me just stop this. Chat. Ravioli. Kidney stone, yes. So let's choose one more time. This is a kidney stone being shattered by ultrasonic sound waves. So everything has a natural frequency that it tends to oscillate at, even a kidney stone. So what they're doing is they're playing very high frequency sound waves that basically match the frequency of the kidney stone, causes the oscillations to start increase in amplitude, eventually to the point where the entire thing can shatter. Okay, couple of just examples of resonance in everyday life. So one, anytime you tune your radio into a specific radio station, you're actually incorporating resonance. So you'll get to this in physics 4B. There's something called an LRC circuit that has a resistor, an inductor, and a capacitor in it. They have a natural frequency that the current will oscillate back and forth at. When you're tuning in your radio station, you're actually changing the resonant frequency of the circuitry so that it matches the frequency of the radio station you're trying to get, and it preferentially gets that radio station over all the others. Mention like pushing a child on a swing, right? If you time your pushes just right, you can get the swing to increase dramatically. Or, just if you guys remember live music, it's been a long time, but if you ever went to a concert and there was really loud bass music playing and you felt this sort of pleasant buzz in your body, irregardless of anything you might have done before the concert, but you feel this sort of buzzing in your body, your internal organs also have a resonant frequency, which tends to be very low frequency corresponding to bass. So if you have a very, very loud bass music playing, it can literally cause your internal organs to start to oscillate at the exact same frequency of the bass music. Okay, that is it for chapter 15. So just as a preview, I decided to skip chapter 16 altogether. I'm only covering one well, let me just say I'm going to touch on waves a little bit, just because chapter 17 is all about interference. And I just want to make sure people are clear on wavelength and things like that. But chapter 17, I'm covering one thing, and that's really just interference. Chapter 15, 16, 17 homework is not due. Friday, there'll be a quiz on chapter 15, what I've covered, and then just that little bit of chapter 17. And then we are pretty much done for the semester. Keep in mind, lab 10, due tomorrow. If you're going to send me a video presentation or formal lab report, due by 11:59 p.m. Preferred method is to get on Zoom and do a 5 or 10 minute video presentation. The video presentation should approximately follow the same order as a formal report. So an introduction. What are you doing? What theories are you testing? Procedure. How did you do the experiment? Your data. What data did you take? How did you analyze it? And then your conclusion. If you were testing a theoretical prediction, how well did it test out? If you were doing something like seeing whether or not certain things obey Hooke's law, what is your conclusion? Yay or nay? And then support that. Lab due. For the labs, just email them to me. Just because especially if it's a video presentation, they're going to be big files. Downloading all of that off of Mastering Physics just literally takes forever. So any videos, any formal reports, email to me. That's it. So I am letting go lecture, bringing in office hours for 20 minutes. Thank you for everyone who joined me live. I will post this on YouTube later today, but I'm going to stick around for 20 minutes to answer questions you have on anything from chapter 15, any lab questions or anything like that.
Hey, I
Joe?
just,
Oh,
go
damn.
ahead.
Oh, thanks.
Go ahead.
So I have a question on lab 10.
Okay.
So I did my I used the idea of when a ball bounces, does it lose the same amount of energy to heat and sound on each bounce?
Yes.
And I completed the lab and I have everything finished, but I'm looking over it again, and now I'm wondering if my process of thought on how I did it was correct.
Okay.
So what I did was that I would find the energy of the ball before it was released, and then the energy of the ball after when it touched the ground, when it bounced, and then I'd find the difference of that to find the total energy lost.
So how did you get the energy? So my thought was you release the ball from rest. So you know it's got gravitational potential energy, mgy, hits the ground, and then goes back up to less of a height. So mgy2. The difference between those energies would be how much energy it lost on the bounce. Is that how you were doing it, or how are you getting the energy right after it hit the ground?
Well, I was using the conservation of energy equation. I would basically I'd set everything equal to ETHY, and then through my values I would find the total energy.
Let me close. Let me share white screen. So the setup is you were dropping a ball from some known height, right?
Yes.
So you know the initial gravitational potential energy was going to be equal to mgy initial. And then it hit, lost some energy to heat and sound, and then went back up. So again, tell me, how did you go about getting the energy after it hit?
Well, I've solved for ETHY, which was my equation, turned out to be mass times gravity times delta y subtracted by 1/2 mass final velocity squared.
And how did you get that final velocity?
I got the final velocity by the distance divided by the time.
So one, can't do that. Anytime you're doing delta x or delta y over delta t, keep in mind this is the average speed, right? Anytime you're doing a distance divided by a time, that gives you your average speed over that time. What you'd really want is the speed right before it hits compared to the speed right after it hits. So if you were using this to calculate the speed, none of your results are going to be accurate because you're not getting the speed right before or right after it hits. What you'd be getting is the average speed over that whole time it's in the air. So here's what I would recommend is you release a ball from rest from a certain height, it's going to bounce up to less of a height. So I know that the energy it had right here was equal to mgy initial. The kinetic energy it has right before it hits, if I ignore air resistance and friction, should still be the potential energy it started with. Then it hits, it loses some energy to heat and sound, and then goes back up. Well, again, if I assume it doesn't lose any energy in going from after it bounces to the highest point, then I could just say the energy right before it collided was mgy initial. The energy right after would be mgy final. And the difference between these two would be how much energy was lost to heat and sound. Because like if it was a perfectly elastic collision and absolutely no energy at all was lost, it should bounce to the exact same height that you released it from. But every time it hits, it's going to go to slightly less height. And if I look at the difference between those two heights, that should be how much energy was lost during the collision.
Okay, I see it. Thank you. That really
Does
cleared things
does
up.
that make sense?
Yeah, that makes more sense because my data was just totally off and I was getting confused.
Yeah, it's totally off because you were using the average speed, and keep in mind it's slowing down or speeding up the entire time it's in the air. That's not going to be useful. You need to know what is the speed right before it hits, right after it hits. But the easiest way is just look at potential energy it starts with, how much it has at the end of each bounce, and seeing if it's losing the same amount.
Yes, and would there be a theoretical prediction for this experiment?
You could. There's something called the coefficient of restitution, which is a number between 0 and 1, which describes how much energy is lost on each bounce. So like if the coefficient of restitution was 0.7, that would mean that after each bounce, it should still have 70% of its energy. But I haven't covered that. There's a couple people that sort of researched that on their own. If you wanted to, you could try and figure out what kind of ball you have, what kind of surface it hits, and you could look that up. But no, you don't need to have a theoretical value for that. So what I'd like people to look at is, one, does it lose the same amount of energy in terms of the number of joules? Or two, does it lose the same percentage of energy? So, you know, every time it bounced, let's say you released it from here, after one bounce, it bounces up to this height, after the second bounce, this height, and so on. You could look at two things. What percentage of energy is lost on each bounce in terms of percentage of it had before, or what total energy in joules is lost on each bounce, and see if it's the same amount of energy or the same percentage of energy lost on each bounce.
All right, then. Thank you.
You are welcome. Clear all drawings, stop this share. All right, other questions I can answer. Can energy loss percentage be calculated with mg? Yes, or it would be, so if mgy1 is your initial, it should be mgy1 minus mgy2 over mgy1. It's how much of the original energy was lost on each bounce. So you should be dividing by the original. So the numerator should basically be the difference in energy. The denominator should be the energy it started with. And you'd be looking at that on each successive bounce if you're going to look at it that way. Other questions I can answer from anybody? Maria, Marco, Leo, Uriel.
I was just gonna ask you more about resonance because I thought it was really cool.
Yeah, go for it.
I don't even know what to ask, but when we were working on our project in Costa Rica on engineering abroad, when we had water going into the tanks, it started to like oscillate like that, like really crazy. And we built like it wasn't our final design. We put like a turbulence shield over where the water was coming in. So in the end, we didn't have that resonance.
So you've got like water coming. Actually, let me share this so I can visualize this. So you've got maybe like a tank or something that's holding water,
Yeah,
and you've got water pouring into it, and then that's causing this water here to start to oscillate back and forth a lot.
yeah.
Ah, very interesting. So that probably was resonance, where the frequency of the water coming in sort of matches the frequency that this water would tend to oscillate back and forth at, producing resonance. Now, let me see if I can share something real quick, because there's another phenomenon like that. Physics 10, this would be chapter 20. Physics, I have so many notebooks now. Physics 10, chapter 20. Okay, PowerPoint slides. Oh, that must be chapter 19. Physics 10, chapter 19. PowerPoint. Ah, all right. Never mind. I thought I had something better to show. So I call this the Calvin and Hobbes bathtub tidal wave, where if you've ever been taking a bath and you sort of move forward and it sends this little pulse of water that then reflects off the bathtub and comes back. If you've ever been in the bathtub, you can create this huge tidal wave by just timing the frequency of you moving back and forth to match the frequency of this water wave moving back and forth. And just by the smallest little pushes, you can get this big sort of tidal wave coming.
Oh, that's pretty cool.
So he did that in some, Calvin and Hobbes cartoons. So I call it a Calvin and Hobbes tidal wave. But yeah, there's lots of interesting examples of resonance. So even like, go ahead.
So when you were talking about the radio, how does it, so I understand like you change the dial, which on your radio station that changes like the frequency at which you're receiving sound waves, I guess.
Correct. Yes.
How does resonance then?
Well, in this case, let me be specific. It's the frequency of the radio wave that you're receiving, which then gets converted into a sound wave. So, I mean, the fact that you can detect, 50 different radio stations means that you have 50 different frequency radio waves at the location of your antenna at the same time. And what you're doing, in essence, is you're bumping up one of the signals by increasing the amplitude of that radio wave signal enough so that you're preferentially picking it out over all other radio waves. And then that radio wave then gets converted into a sound wave with the speakers oscillating back and forth at whatever frequency so you're converting a radio wave into a sound wave by the speakers. But
okay.
The resonance is changing the circuitry's internal resonant frequency to match the frequency of the radio wave that you want to tune your station to.
Oh, so that's what the dial on your radio is doing. It's changed. It's like creating resonance with those ones.
Right. And I had another example I didn't mention, but I had a car back in college where every time I'd hit about 52 or 53 miles an hour, I'd have this super annoying rattle in the car. And what it was is there was a loose nut somewhere. And again, even a loose nut has this frequency that it would tend to oscillate back and forth at naturally. And it just so happened when I was going about 52 or 53 miles an hour, the car would shake at a given frequency that matched the frequency that this nut would unnaturally oscillate back and forth at. And so it started oscillating more and more. And then once I got above like 60 miles an hour, it would go away. So
that's so funny, because
it was this narrow range of speeds that would cause this thing to oscillate back and forth, and it would freaking drive me crazy.
That's exactly my car. That's so funny. I have something exactly like that.
So if you could somehow figure out where that sound is coming from, it's going to be a loose nut or something, and you just need to tighten it or put something on it so it changes the frequency that it wants to oscillate back and forth at, so it's not matching the frequency your car is oscillating at when you're going at a given speed.
Cool. That's really interesting.
Yeah, it's
Thank
super
you.
interesting. You're welcome.
So also, I have a question for 10, since I'm doing the Hooke's Law one. I don't have a theoretical value to compare it to, correct? My theoretical value is that K is going to be equal for all.
Right, so you're really just testing, does a rubber band or whatever you're looking at, does it obey Hooke's Law? And I don't know the answer. Like, okay. I don't know whether specific kinds of rubber bands do or don't. And so, yeah, your conclusion would be, here's the data. You can see that it's linear, so it obeys Hooke's law, or it doesn't.
Okay, thank you.
You're welcome.
Hey Joe,
Hey,
can you hear me?
I can.
Did you end up checking out my lab, or?
No, I'm so sorry.
Oh, it's all good.
And you know what? I'm about to pick up my daughter. Your just question was whether you need to do anything else?
Yeah, I mean, at this point, just like I figure, like when you're grading it or something, just like let me know if I need to present tomorrow or something.
You know, at this point, I'm about to go get my daughter. I have her all day. I don't think I'm going to be able to do it. I told you twice that I would look at it, and I totally spaced. So you're fine. Even if
I mean, I can present if you want. I just don't know.
Okay, if I get a chance, I'll look at it. But yeah, I'm not going to have a lot of time once I end this. And so if you don't hear from me, assume you're okay. And I apologize for saying twice I would look at it, and I didn't. I just, yeah, I totally forgot.
No, it's understandable. We all got like a lot of stuff going on these days.
Yeah.
So, yeah. Well, then I guess I'll see you tomorrow.
Okay, sounds good. Thanks, Marco.
All right. Thank you. Have a good one.
You too. Hey there, Ural. You have any questions? I'm going to end this in about a minute, if not. Going once. Going twice. Woo! Office hours done.